Hello again everyone and welcome to another episode of Freaky Physics. And yes, we are back. We're trying to do these things. I haven't shown them yet how to do minimum and maximum lines for graphing. So, here's an example. I have some simulated data here. We're looking at the resistance of a piece of nichrome wire and how it varies with the length of wire that carries the current. We're going to skip over what we got because this is simulated data. However, it's going to be enough for us to say that we have measured the lengths, the potential difference across the wire, and the current through the wire. And these are the values. We have also put in here some uncertainties. As you notice, we are using a Google Sheet. Google Sheets, unfortunately, has this limitation of using error bars. They can only do a certain value or a certain percentage or the standard deviation. Since in IB we don't do standard deviation, that's out of the question. We cannot do percentage because they all have different percentage uncertainties per value. We also cannot actually use a set value. We can have different values for the uncertainties. What we'll do here is what we'll call a hack in terms of how we're gonna record our data on the graph. If we look here, we have recorded the data. But earlier, our length data was in centimeters and we have converted it to meters. For those who are not aware, we can convert our centimeters via formula to get our meter lengths. In this case, we simply divide by 100 to go from centimeters to meters. Now, you can see that this is a little bit of a strange formula here. But basically, if we look back on our raw data, B4 is the uncertainty in L and A4 is the actual length in centimeters. The reason for this is simply because the percentage uncertainty in the length doesn't really change. Because we didn't really do anything except change the unit. So all I'm going to do is change the uncertainty via a formula. This is going to give us 0.5 over 5 for the uncertainty. Then the percentage uncertainty would be 0.5 over 5, which is 0.1 or 10%. That 10% is going to go into here, and this is what we get. So this is our 10%, and our value for H4 is the value for the length. So now that that's clear, again, you can calculate uncertainties via formula, or if you already have values, you can use half range you can use whatever method you see is appropriate. But anyway, you see here that on our data here, R equals V over I. So that's what we're going to do here. The formula here is V divided by this. Of course, via formula, so the next one will be this divided by this, and so on. We get these values. We got these values for the uncertainty via this formula. You're dividing V over I in this case. So this means we're going to add percentage uncertainties to get percentage uncertainty in R. So if we look at the value here, you can see that all I've done is taken E4 divided by C4. It's the percentage uncertainty in V. And then we are adding to that F4 over D4, which is this and this. So we're again taking the percentage uncertainty that's equal to the percentage uncertainty in the resistance. But we have a resistor. We can get the absolute uncertainty in R by multiplying this bit, which is the percentage uncertainty in R, times the actual value of R. You must remember that uncertainties must be expressed, at least in the IB, to one sig fig. So we have to do this. These guys, this is still 2 sig figs, and then these guys are 3 sig figs. The important thing here is that all of these, they have different values right here. One more thing before I forget. This is 4 decimal places, but our value for R is 3. We're going to have to convert that to 3 decimal places as well. Decimal places must match. Similarly, these were actually that. But 2 decimal places in the uncertainty, our R's must have 2 decimal places here. Hence, we get these values. We're going to graph that, and in this case, that's this blue dots here, and its trend line is already exposed here. Now you will notice we also have a red and a yellow line and dot, but it doesn't really cover everything else. This is here. What we've done is I am graphing only the resistance for the maximum line and the resistance for the minimum line. The easiest way to do that is this. You can do it one of 2 ways. Let me clear this out first. What you can do is you're gonna get the resistance and you're going to add here the uncertainty. The next thing we can do is here, we get the resistance, then subtract the uncertainty. There we go. Let's do this part. What we're going to do now is we're going to reverse. Here, we added the uncertainty. So this means here we subtract, and also here we subtract. So what we're going to do is resistance minus the uncertainty right there. And finally here we're going to do the reverse. So this is going to be resistance plus uncertainty. With those in mind, you will actually graph these. Okay, I'm going to delete this graph for now. You can see here again that in Google Sheets we have different uncertainties, and as I mentioned, we can't do custom error bars. We can only have like a generic custom bar for the whole graph. The workaround there is to use the biggest uncertainty you have to put in your error bars. Of course, we don't want lines, so we'll change it first to scatter. And you can see we have lots of different possible values. The x-axis will still be the length, so that's okay. However, we don't want the uncertainty in the graph, so we'll remove that. We want the R in ohms, the resistance. We don't want the uncertainty in VR, so we'll remove that. But we do want these two, R4 max and R4. Once that's done and we have our scatter plot, you can see that we have two other dots there. The next thing we're going to do is we need a scatter plot. We do best fit line. Now, in this particular example, we already have a very linear graph. All we have to do now is go up here. When you open the series, make sure you do this first for all series. The only thing you need to do for all series is the trend line, and you need the equations. You may put r squared, but I would recommend not. You don't need r squared if you're not doing statistical treatment. The next thing we're going to do is here, go back here and change to the actual graph. Once we go there, we go back down and we put error bars. We can only have standard deviation, which is a relatively new feature. We can have percentage, we can have constant, or we can have no error bars. We cannot have custom error bars. So what we'll do is we'll choose constant and we'll use the biggest value of the uncertainty in what we have, which was 0.08. Let's take a look at the graph. So how would you interpret this graph physically? So this was the experiment that we did. What we want is this length here, and then we measure this V, and then we measure this A. The current here, and the potential difference here, and this length here. And once we measured that, we calculated the resistance from V and A. Once we have all the data and we graph this, let's take a look at how we can interpret this. Once we have a linear graph like this, we can always take the slope of the line or the gradient of the line and then its y-intercept. We're going to look at the relationship between the length and the resistance of a wire. It's given by this equation. And since we have graphed the length on the x-axis and r on the y-axis, then we can already say here that resistivity divided by the cross-sectional area of the wire gives us the gradient. We can now figure out a few things. First of all, because of this formula, we can now say that the percentage uncertainty in the gradient is equal to the percentage uncertainty in the resistivity plus the percentage uncertainty in the area. In this case, we have assumed that the diameter of the wire was constant and had no uncertainty. We didn't measure it. So that means the uncertainty in the area would be 0. Since that's 0, I just remove that. The uncertainty in the resistivity percentage-wise is also equal to the percentage uncertainty in the gradient. How do we get this? This is where your best fit line and your lines of maximum fit come in. The gradient is 15.1, 15, and 15.2. The uncertainty here is half range, 0.1. Equals 0.1 divided by 15. Turn that into a percentage, so 100 times. 0.667%. Since this is the percentage uncertainty in the gradient, this is now also the percentage uncertainty in the resistivity. Which means the resistivity itself, whatever value we got here, which is 15.1, that's going to have a very small percentage error, which means the uncertainty is negligible. Second thing we're going to look at is we can actually also calculate the actual resistivity, and then from that we can calculate the absolute value of the uncertainty in the resistivity. But because of the small percentage here is going to be negligible as well. We have just figured out from the uncertainty what the resistivity is and what the percentage uncertainty is. In other words, this graph supports the fact that the data is very well collected and that the small percentage uncertainty in the resistivity and in the gradient. On the y-intercept, remember that the x-axis is length and the y-axis is resistance. You would expect that when the length is 0, in other words, you don't have a y, you will not have a resistance. Now, let's take a look at what the y-intercept itself is. The y-intercept, when you calculate it, it's right here. 1.44 e to the minus 3. In other words, 0.00140. It's a very small value compared to the actual values we have on the graph. We have 15 the maximum. So that means this is already negligible. The y-intercept error is already negligible. We can also further calculate the absolute uncertainty in the y-intercept. This covers the expected 0 ohm value, and again, on its own is very small. But what's the percentage uncertainty? And this is where it becomes interesting. Percentage uncertainty is 362%. How do we do that? Uncertainty divided by value. That's a big percentage uncertainty. But the fact that we still have a tiny absolute value means we can still actually make sure this is negligible. You don't rely only on percentage uncertainty. You don't rely only on absolute uncertainty. You must rely on the combination of the two things. So that's how you would do the graph. Don't forget to like and share this video and to subscribe to the channel via your preferred social media platforms. Visit the website for more information. Stay freaky, everyone.